His group has done a lot of the sort of pioneering work on offline handwriting recognition, especially used by, and it's the core of what's used by the U.S. Postal Service for sorting all of the mail that gets delivered automatically. So.
Okay, thank you. Good morning, everyone. I'm very happy to be here. And this talk is essentially going to be more of a background covering of what we have been doing at University at Buffalo for almost 20 years now. And so the way I've structured this talk is to give you a sense for what we did over these 20 years, give you a sense for the size of our group, the kinds of topics that we have been working on, and also give you a sense for the expertise that we have so that we can come up with some joint projects with Google. So so the title is Making Sense of All Things Handwritten, from Postal Addresses to Tablet Notes. So as was mentioned in the introduction, we have primarily focused on offline handwriting recognition, and that stems from our postal automation work. But recently we have been very interested, with the popularity of the tablets, to look at online handwriting, and hopefully we'll find, some common ground over there. And so at the end of my talk, I'll come up with a proposal, like a teaser, saying this is what we want to do, and hopefully we can come together on that. So starting, handwriting is back. For quite some time now, we have been hearing, with the PCs and everything, and everybody just using the keyboard and typing and emails, that handwritten mail has gone down in volume, that maybe handwriting is not that relevant anymore. But actually, as an ironic twist, these same technology things like tablets have brought handwriting back to the forefront. So I just picked this up, on the web. So let's see. Again, handwriting is becoming relevant. This was an article in the Wall Street Journal which said that handwriting actually helps train the brain. So when kids, instead of just typing, looking at a symbol A, B, C, and just typing them, when they are actually using motor skills to draw those characters, there is a learning that is happening, and that is very important. So this was quite recently. Again, another article saying the many health perks of good handwriting, right? So we feel, handwriting is going to be back, especially given, the popularity of the tablets. So here are some examples, just to get started with the motivation for offline handwriting recognition. Here is a letter. We can all see it's signed by Einstein. It's very difficult to actually go and transcribe that today's technology, right? So still the challenge is out there. If you wanted to do complete transcription of handwriting such as this, we don't have the technology there yet. This is another example, and now you can guess, since I showed Einstein in the first example, this is from, I believe, from Newton. And these are all historical documents, right? So here, it's even challenging to just have a viewing, right, so that people can read. So just to, how do you enhance this image? What kind of context can you bring into play over here so that people can just view it properly? This is actually a letter, I think Washington's letters, which I'm told were actually not written by Washington, but by his secretary. So they all looked alike. But here the handwriting is much nicer, where there were special secretaries dedicated to writing letters, right? But once again, if you wanted to do complete transcription, this is not going to be easy. Then the most challenging of it all, the doctor's handwriting, right? So this is again the snippet from a medical form image. And you can see it is not purely cursive, it is mixed, discrete and cursive. And once again, the handwriting is quite sloppy. So with that background, so handwriting recognition is definitely not a solved problem. Sometimes when you go to, different sponsoring agencies, they feel that handwriting is a solved problem. OCR is all done, and there's nothing much more to do in terms of research. But as you could see from those examples, we have a long way to go. So let me kick off this talk by first showing how we actually came up with a working solution for the Postal Service. Okay, and that should give us an idea on how maybe we should move forward when we address some of these challenges. So this is an example of a mail piece. This is Edward Kubert. He was our sponsor from the Postal Service, handwritten address. So the task here was given the input, which is the address block image, which in itself could be a challenge, right? Locating the address block on a mail piece could be challenging if it's like a magazine cover or something with other kinds of graphics on it. Locating the address itself could be a challenge. But let's say we have a nice clean address block image. The objective was to come up with an output. So you take that as an input, and the output should be a barcode, okay? And that corresponds to an 11-digit number. So using 11-digit barcode, apparently you can have a delivery point code for all the addresses in the US, which is about 250 million, okay? So this is well defined. You have an input image, you give me back 11-digit code, okay? So in that sense, this is an interpretation task, input, and we know the correct answer for that input, okay? So we have to process that address image, generate that barcode, and then there are barcode sorters which can sort this, okay? So just a quick background over here. So the way the Postal Service used this technology was by what is called a remote computer reader. So like millions and millions of mail pieces every night. So a post office like Buffalo would see more than 1 million mail pieces a night. Okay. So the images are captured, right? And if you can actually come up with the 11-digit code for those mail pieces, by the time the mail piece actually goes over the belt, which is about 20 feet over there, and you have an answer, then you can spray that barcode and you're done. But for most of the mail pieces, you're not able to do that. So what is done is you take the image, you put a barcode on it on the reverse side, which you must have seen in the pink color, it's a fluorescent code, which essentially tags that mail piece, keeps it aside. The image of that address block is sent somewhere else, wherever there are keyers in the country, right? So there are various keying centers. The images are sent to the keying centers. So the keyers will type it in. So then the corresponding 11-digit code is sent back and slapped onto that same the mail piece, and then it is sorted. Okay, so that's why it was called remote computer reader. And this way, what they could do is they could, in some sense, as the recognition rates improved, the number of keying centers went down. Okay, so that was essentially the idea of the remote computer reader. So we have been touting this as a major AI success story. In fact, even in the earlier pattern recognition conferences, this happened in 1996. Actually, that was the first time when the US Postal Service was able to read handwritten mail piece addresses by program. So the first time this was deployed and it used our technology developed in our lab, we were able to get about 15 to 16%. Okay, and that in itself gave the Postal Service several $100 million of savings because of the volume of mail. So from there on, over the years, you could see this is an older graph. It's almost 10 years old, but you could see that it was already moving to about 70 to 80%. Today, about 97% of all mail, whether machine printed or handwritten, is completely read by a program. So the image is being taken and the barcode is being sprayed. No human being is actually reading the address and interpreting it. So there are no keyers for 97% of the mail. Okay. So this, we believe, is a major AI success story. And the key to the success was the following. If you gave me a task today and you said, well, you can solve the postal problem, can you read this Einstein's letter or Newton's handwriting? And clearly we cannot. The reason we were able to solve this problem in the postal context was because of the use of small lexicons. Okay, so this shows you some recognition rates. Like when you have the lexicon, which is small, about 10 words in the list, you can do 97% recognition. Okay, so what we did, and this actually worked very well in the postal context, was you have the directories. So you have the postal directory, which tells you what are the zip codes. So 5-digit zip code means out of the 100,000 possible, there are only 50,000 which are valid. So there you have some constraints. And then different zip codes have different number of streets that are there, right? So given the zip code and the street number, we found out that on average, you have only about 20 street names possible. So you give me the zip code and you pick up a street number, there are only, on average only about 20 street names. So that becomes my constrained lexicon. So given that you can do numeral recognition with fairly good accuracy, right? And it's only 10 class problems, 0 to 9. If you have recognized the zip code and the street number, then you have a constraint, the lexicon. And in some cases, you actually have only 1 or 2 streets possible. So that is what we used. And so here is an example. We have an address block over there. So we recognize 14213 as the zip code. You recognize 74 as the street number. Then you use the postal directory using the zip code and the street number, query the postal directory, and you get back about 15 streets. Okay. So now the word recognition task is reduced to taking the snippet of the street name over there and matching it against these 15. Okay. So in this case, it is Livingston Street, so 1653. So the zip plus 4 would be 14213 1653. That makes it 9 digits. And then the 2 additional digits are the last 2 digits of the street number, 7 and 4. So that gives you the 11-digit delivery point code. So in some sense, you have 250 million addresses. Any of those could have been possible output. You give me an input image. So from 250 million class problem, we are actually able to reduce it down to about 20 class, 15 class problem. And that's how we were able to solve this. Okay, so it worked very well with small lexicons. Now, if you look at this whole task of postal automation, actually it has a whole bunch of pattern recognition tasks, subtasks, right? So the first was address versus non-address, like a segmentation task. Machine printed addresses versus handwritten addresses, the classification task. So we were involved in the handwriting address interpretation, which used to be about 10% of the mail. Even today, the most interesting mail that comes to my mailbox is the handwritten mail, because the rest of it is mostly advertising, right? So, but it was 10% of the mail, but given the volume of mail, which is unfortunately for us who work with the Postal Service declining, it's still a very large number. And so any improvements we could make with the handwritten address interpretation was translating to immediate savings for the Postal Service. Over the years, we remember, numbers like for every 1% improvement in accuracy, Postal Service was paying something like $10 million. Or for every 0.1% drop in error rate for the same recognition was another 10 million and so on. So a lot of money involved here because of the volume of mail. We also took this technology and through Lockheed Martin, actually deployed it in UK and Australia, for Australia Post and UK AI. So you can see it has a whole bunch of subtasks which all relate to pattern recognition. So you have character recognition, 10 class, 26, 62. Unconstrained handwritten word recognition. The lexicons here are dynamic, right? So unlike the bank check recognition problem, which was also kind of solved a few years back, there the lexicon is static. You have the same words appearing on the check, right? 1, 2, $100, cents. So for some people, millions. So in this case, the lexicon is dynamic. That means every time you give me a zip code and street number, a different set of words are showing up in the list. Okay, so that's something unique about this problem. And then the task of interpretation. Okay, so what I'm going to do is, just to give you a sense for what we have been doing at our lab, and I also want to cover, the full 20 years in the next half an hour. So I'll just pick a few of these, okay, and go into some detail in about 3 topics over here, so that you can get a sense for the kind of research that we are involved in. I like to put up this table, and this is an old table. It's almost 15 years old. And the reason I put this up is when we were designing these algorithms, which actually worked in the field, right? So in 1997, the code developed by students and researchers in our lab was actually used as is by Lockheed Martin. And it was deployed first in Tampa, Florida, and then in all the postal distribution centers in the country. So Lockheed Martin simply got object libraries. Okay, so we are very proud of that because the first time it was deployed in Tampa, and we were told that our funding will be cut if it doesn't work, because then we would have to give everything to Lockheed and they would manage everything, and we were like this, fingers crossed, and it worked actually without a glitch. And I'm told even when the pros come in, there is always something or the other they need to fix. But this code developed by many, maybe 50, 60 students and researchers in our lab actually worked. Okay, and we got about 15% recognition rate. So I'll show you there are many heuristics in that system, okay, which now we have gone ahead and improved, using some more sophisticated techniques. But in those days, we would also report things like how much time it takes to recognize one character. And we would also report what time it took to train the algorithms, right? So some of these neural nets and other things, Darshan would remember, he was in our lab then. You would have to set it up for the weekend, right, for the training to get done. So there were a lot of limitations in the kinds of algorithms that went into this system. Okay, but as we all know, so just points that out. I wanted to show you very quickly in just two view graphs the kind of heuristics that actually went into the system. So here you can see things like the subset of A21 of pixels in A2 whose intensities exceed TZ. There are lots of rules like this, but the system worked. And again, for numeral recognition, there were methods where you had more things like this is describing, some rules for the digit 0. Okay. Combination of recognizers. Again, we had, ad hoc rules such as this. So we had two different recognizers, WMR, like one word recognizer, CMR is another. Okay. One of them is lexicon driven, the other one was lexicon free. And we would have things like you take the entire lexicon, let's say I have 50 street names. You send it to the first one, then depending on the confidences you got and some thresholds, you pass on the smaller set to the next one, and then you finally have a holistic recognizer to do a final confirmation. This is the answer. Can you just check that it has the right number of ascenders, descenders, length, and so on before I accept it, right? Because we always had to maintain a low error rate. So when we recognized 15%, the error rate was still less than 2%. What it means is 85% still goes to the keyers, 15% we returned answers on, and we were 98% correct. Okay, so you had rules such as these, built into the system. But then, of course, over the last decade, we have seen a confluence of technologies, lots more data, cheap storage, processing power, and so on. And, the algorithms have actually improved. So this is going to be the outline of for the rest of my presentation. We will look at pre-processing, handwriting recognition, classifier combination, and some search applications. I will go into some detail in the hand-machine segmentation because that is a recent paper we published and presented at IGDA. It won the Best Student Paper Award. So I'm going to talk about that. Active character recognition. This was presented at CVPR almost 10 years back, but we think it has some very cool ideas, right? So I'm going to talk about that. Classifier combination is something that we have been working on. It's ongoing research, and we have come up with some new identification models. So I'll talk about that. And then finally, in search, we'll look at some keyword search methods, and what the community is doing and how we are doing things differently. So just some quick examples, binarization, rule line removal. So you can see the Markov random field approach that we have used, was published in PAMI, just to show you some results. This is from the MadCat project we have as a subcontract from BBN. This is the DARPA project looking at Arabic handwriting. We have also worked on Devanagari and Japanese and so on. So this should just give you an idea. And this actually entered the competition at IGDAR 2009 and was ranked #1. So the task is to do the line separation. And you can see that it does a fairly good job. More examples of line removal, enhancing the quality. So over the last 10 to 15 years, we have actually gone beyond the techniques that we implemented and were used by the Postal Service. So I must mention that while we had our first handwritten address interpretation system used by the Postal Service in 96-97, over the years now it's actually Parascript and other companies who work with Lockheed, and they do some combination, and clearly, on our own, we would not be able to reach 97. Okay, so it's essentially a combination of different systems. This is again an example to show you even when the lines are touching, we can do some intelligent splitting and the lines. Okay, let me give you some more detail on this particular topic, which is hand versus machine. Okay, so you have a memo such as this. It's mostly typewritten, and there is handwritten matter on that document. So the task is to label the different components as being hand or machine, and then this third category, just noise. So what we do is, the first part is segmentation. We do some dilation and erosion so that we have patches. So you have a patch so that the word machines will be a single patch. And then for those patches, we'll find the labels. So the blue is the machine, red is hand, and then noise. Okay. So unlike what we had in the HWAI system, where we had just a bunch of heuristic rules, and it was all targeted for the male piece. So we would have things like if it's on the top right corner and it's so many pixels from this and that, so it's likely to be a machine or a hand. We have tried to do something more principled over here. So you have 30 real valued features for these patches. So for example, number of pixels with intensity changes in the vertical and horizontal direction, that's one of the features. Maximum run length in vertical and horizontal directions for that patch, that's a feature. The number of components within the patch, a feature, and so on. So we have 29 such features. And then during training, what we would do is, we will come up with the first labeling. Okay, so we take the training data, we do the clustering, and then each of those patches will be essentially put into, given the labels of machine, noise, or handwriting. Then we use, so that part, we are simply observing the features, and only based on the patch features, we are coming up with the initial labels. Then we use the MRF model, where we say that the neighboring patches are likely to have the same kinds of labels. So this is all standard for most of you. So then we have a model where we look at, the xi age essentially will model the neighborhood similarity, and xi o the observation based on the observations. So for each of those hidden nodes, we'll observe for those patch what are the features. So based on those features, we get the xi o, and then based on the neighbors, we'll get the xi age. So this is something that we presented at ICDAR and won the best student paper in Spain. So we can model the observations and then the neighborhood, using those formulas over there. So the neat idea over here was we were also able to look at the spatial as well as the distance in the spatial domain as well as in the feature space. So if I'm looking at the patch confirmed, I'm going to look in the document, what are the distances from that to its neighboring patches. So to the broad, against, indeed, judge, and so on. Okay, and I'll look at the dominant gap between words and lines and come up with a formula such as this, which is like a non-linear thing. So it's not just the linear distance, but it also captures, the dominant gap and so on. So now we can do the relabeling. So essentially that particular patch neighbors using that same formula. So we are looking at the distances both in the feature space, as you can see the D sub E and the D sub H, I think, in the spatial domain, and that both of them together will essentially give me the neighborhood model. So we were able to get significant improvement on the UMD documents, and you can see for precision and recall, for the handwritten matter, we are getting a huge jump on the precision values. But that's kind of expected. And you might say, well, what is so great about this? But you have to understand the culture from which we come, from a whole bunch of heuristic rules, which is essentially how much of the document analysis recognition field is going. And now, you can see that the approaches are much more principled. Now, let me talk about handwriting recognition. Okay, so we'll look at active character recognition. So here the idea is as follows. So if you recall, we said that in the Postal application, we are looking at dynamic lexicons, right? So we would like a method which adapts based on the lexicon that is presented. Okay? So in most cases, what would happen is you have the classes given, and then you have features based on that, and you use the same features every time, and then you have the same matching and classification. But we would be interested in something where the feature selection and the matching and everything adapts to the kind of lexicon that is presented. And I'll explain that. So if you look at the profile of the word over there, and if I asked you which city word it is, you may not be able to guess, but you know I'm coming from Buffalo, and you might say, oh, it's Buffalo. But if I gave you the choices, let's say the 3 choices were Amherst, Buffalo, and Boston, then you could look at the lexicon choices and then go and eliminate some. You could say it cannot be Amherst because Amherst does not have a descender, and I have descenders here. Well, it could not be Boston, again, no descenders, must be choice B. Okay, till I give you another choice called none of the above, and then it gets confusing like all multiple choice questions in exams, right? Till you give me none of the above, I can start guessing, but once there is none of the above, guessing becomes difficult. But that's essentially the idea. So we want to extract, let's say I had 2 competing choices in the lexicon. I would look at those entries and then see which features would discriminate these 2, and then go and extract those features. Or I might have a whole bunch of features at my disposal, and I'll use that particular subset which best discriminates those 2 classes. Okay, so that's the idea here. And this idea was actually used by McClelland Romelhart. Earlier on, there was a one-way interaction where, let's say in this example, they were looking at horizontal strokes, vertical, and the diagonal strokes, and that would trigger different letters, and different letters would trigger different words, but it was always going one way. What we would like is a 2-way interaction. So I will extract a whole bunch of features, but I'll wait for my feature selection till I see what lexicon choices are competing. A good example for that would be if I gave you a lexicon where all the entries in the lexicon had the same length, then length is clearly not a good feature, right? So here is an example to take that further. Let's say we have 3 numerals, 3, 5, and 7. So given the context, somehow we have figured out that it can only be 3 or a 5 or a 7. Maybe I read the city name, and so this is a particular position in the zip code. It can only be a 3 or a 5 or a 7. Now, if 3 and 5 were competing, then you can see that the lower part is pretty much the same. Okay, it's the upper part which is different. If 5 and 7 are competing, it's the lower part which is different. So my feature extraction selection should be adaptive, so that after looking at what choices are available, I go and have higher resolution in those parts of the numeral image. Okay. So we implemented this, by looking at some 9 features. So there are some moment features and some. Essentially, what we do is we look at some critical points on the contour of the numeral, and then we join them by line segments, divide it into 4 or 5 areas, sub-areas, and then we have features such as how many of those line segments are in which directions. Okay, so of the 4, and then you have a binary vector. So we have a 9-feature vector corresponding to each of these. So the way the adaptive part comes in is depending on the choices that are available, I will go and again take, let's say I'm looking at 3 and 5, then I'll go to the upper part and take each of those sub-areas and divide them again into 4 or 5. And again, look at the same features. So now what I have is, I have some kind of a tree, right? So I'm taking nodes and then I'm dividing them into 4, and then certain nodes are being expanded. So at any given time, I have a particular path through the tree which represents the features that I'm using and at different resolutions. So this node is getting expanded into 4 before these nodes are expanded, which means you are going into a particular area of the image. And this selection on which node is going to be expanded is based on which classes are competing. Right? So if I have 3 and 5 competing, I'll expand a particular node, 5 and 7 a different node, and so on. So this is the adaptive method that we used. Then we actually then took that same method for word recognition. So this is what we call the lexicon-driven recognizer, where you take a word image, you segment the word image into at potential character breakpoints, and the assumption is that no character should be broken into more than 4 parts, no 2 characters should be left joined together. So then you have those segments, you have corresponding nodes, then it essentially becomes a graph problem where you have arcs jumping up to 4 nodes because of our assumption. And the idea is you have to go from the first node to the last node, account for all those segments. Okay? And then there is a cost associated with each of those arcs. This is lexicon driven because at each stage, the question I'm asking is not which of the characters from A to Z is it, but I'm simply looking at the lexicon choice I have at hand. I take that first character and ask the question, is that first segment a good W, right? Or is it a good O, good R? So that's how I'm having the lexicon. Now I could look at all the lexicon entries. I can look at all the first characters over there and then decide, which features to use and, go through this graph. Okay, so the next topic I would like to go over is classifier combination. So in classifier combination, whole bunch of heuristic methods are actually available, right? I mean, even today you will have the sum rule, product rule, where the rules are fixed, irrespective of what the data is, what training data you have. They essentially have a whole bunch of rules. They try out these different rules and then zero in on one of the rules. So what we have done is we have tried to see if we can actually derive that combination function f. Okay, instead of having it as a predetermined function, what is that function f? Can we learn it from the data? So here is an example. So you have m matchers, and let's say you have n cities. Those are my classes. So you get a score matrix. So matcher 1 essentially gives you scores for all, given an input image, it's giving me scores for all those cities, matcher j and matcher m. So traditionally, the way combination would work, and these are the type 3 where we are actually using the scores. So you have the ones which don't use, simply say yes or no, the others where the rank is used, and the third where the scores are being used. So we are looking at type 3. So usually what would be done is for each of those classes, you will look at all the scores, so the columns, and come up with a combination f, which combines all those scores and gives you a new score. Okay, and that is what will then be compared. But keep in mind that you also have the other scores available. Okay, so actually you have all these scores available for each class also if you could use it. Of course, the modeling becomes much more difficult, and coming up with that function f is also more difficult then. So if you look at the two tasks, in biometrics this is quite common. We say the verification task and the identification task. We also have it in documents and handwriting. So if you recall from the Postal first combination thing that I showed you, finally when I have an answer in hand and I want to spray that as a barcode, I want to do one final check, right? And that's my verification task. And that could be, my answer is buffalo. Can you just make sure that the image does have the descenders and ascenders and the right length and so on? So there the answer is simply, output is simply accept or reject. In the identification task, you want to rank all the classes. Okay, so there are two different objectives over here. Now, what we discovered, and this is not, this should be actually obvious, although it was kind of missed in the literature for quite some time, and that is that most people will assume that, okay, you have a neural network and SVM or something else, and they will assume that these are all independent, and then they'll go and combine the results from these classifiers. However, in all these cases, the input image, the signal is the same, so they are probably looking at the same kinds of features. Okay, so they're not truly independent. So when we do biometrics, we say true independence is, and maybe that is not true independence, is if you're doing iris comparison with fingerprint comparison. So you're combining fingerprints and iris, so the signals are different, algorithms are different, everything is different, and then you can have that assumption. But even given that these matches are independent, what we noted was that the scores returned by that same matcher are actually dependent, right? So if you give me a poor quality input image, chances are that all the classes, including the true class, is going to come back with a poor score. And if the quality is very good, chances are even the imposter classes are going to have decent scores. Okay, so that is essentially what we try to exploit. So here you can see this is independent fine. That means the different matchers are giving you scores for the same class. Let's say they are independent. But how about the scores given to the different classes by the same matcher? That clearly is not independent. Okay, so with that insight, we actually looked at the verification task, and this has been shown in the literature, and it's quite easy to derive that the likelihood ratio function will actually be optimal, for the verification task. So here we are looking at two different word recognizers, and then we implemented the likelihood ratio, and we also did a weighted sum where we say, okay, let me give, alpha weight to the first one, beta to the second, alpha plus beta is 1, and I played around with it, had a validation set, came back with an alpha and beta, and then did the combination. So you can see in this experiment, the likelihood ratio did well. However, the surprising thing was that when you use that same combination function in the identification task, it actually doesn't do well. So here you can see lexicon free recognizer on its own, Venu recognizer on its own, both are correct, either correct. Likelihood ratio, actually the combination goes worse than one of those recognizers. Okay, and we believe that this is because the likelihood ratio, if you implement it for the identification task, it starts assuming that you have independence across the scores written by the same matcher. And that's the flaw, and that's why you have a drop. So how do you account for this now? So there is no closed form optimal combination function for the identification task, not that we know of. But there are some iterative techniques, and we have implemented some. But this shows you that same example. So you have a poor quality input. The different classes can get these scores, good quality scores. Take note that in this case, the top choice score is less than the imposter score in that case. Okay, so if you want to have a combination function, you should keep that entire score vector together in your training. So when I'm training, I should keep track of what was the genuine and the corresponding imposter scores for a particular trial. So I give an input image, I got all these scores for the true word and all the imposter words. I keep that whole vector together. And that's how I do my training, so that the dependence between the scores is captured. Okay, and this is also in some sense capturing the quality of the input. Okay, and we have and others also have looked at the difference between the top two scores as an indicator of how confident you can be. Right, so if there's a huge difference between the top and the second, you are more confident than when they are very close together. And we did some experiments using that same model and saw improvement. This is this is an iterative algorithm example where we look at the entire score vector, keep it together, and on every trial we'll update these parameters, and always ensuring that the genuine score should always come out on the top during training. And we came up with this, and this does fairly well, much better than the likelihood ratio. So we have actually quite a few papers in this whole area of combination of classifiers, published in IEEE Transactions. That was just to give you a sense for where our research is going in that area. Now the last topic is on search. So everything is search today, right? All our interactions with the computer is about search. So in this, when I started my presentation, I said there are very challenging handwritten documents out there. And although we say that we have solved this postal application and we can do bank check recognition, we actually cannot go and transcribe Newton's handwritten notes. Okay. So what is it that we can do? Well, we should at least be able to view these documents. So I can go and type Newton's notes on gravity, and his original notes, probably some library in England, should be viewed, and I should be able to read those as images, right? But right now they're historical, they're poor quality, and even reading is difficult. This is one such historical note. As you can see, it's kind of degraded. But if you do some, oops. Oh, yeah. So you can see some enhancement. And now I can actually read, I hereby assign something conveyed to James, and so on, right? So at least this we should be able to do. And we have techniques to do this enhancement today. These are palm leaf manuscripts actually provided to us by Michael Lesk to see what it is that we could do with these. And again, just for viewing right now, not for recognition, you can see we can repair the strokes and do a good job of making it viewable. We also started, actually we introduced this problem in 2001, where we said, what if you actually have the transcript? For many of these historical documents, historians have actually transcribed what is there on these documents. And I would like to view them side by side. Fine, that's not difficult. You show me the image and you show me the transcription. It would be even nicer if there is a mapping from the word images to the actual transcription. And that's interesting because then I can take my mouse over certain words, click them, and they can be hyperlinked. So also it gives great truth data for our OCR tasks. So the transcript mapping, we presented, and then since then there has been quite some work in the community. So this is the transcription, and the task here is, you take the snippet. So you have the word segmentation problem because the gaps are different, the words could be broken, line breaks could be different, and how do you come up with the best mapping? Okay, so this is also possible today. So what is it that we want to do? So well, we looked back and said, let's see where our recognition is in our lab. Okay, this is all offline so far. So if you give me good quality images, okay, and large lexicons, I can do about 50 to 60% top choice recognition. Okay, and as you increase the top end, recognition will improve. But if you go for poor quality, you can see we're in the 20s and 30s. Now, from my friends and colleagues in the speech community, they said you need to be around 70% recognition rate to actually have a satisfactory user experience with the search. They said there are two things going for you in search. One is that you are not necessarily going to get the top link. As long as you are somewhere in the top 10, you have done a good job. And also, if you're looking for words in a document, the same word might be appearing many times in the document. As long as you got one of those, you will be able to retrieve the document. So given these two things going for you, around 70% recognition will give a decent, satisfactory experience for the user. So if you look at these lexicons, the general English, let's say commonly used words would be like about 100,000. For 10,000, we are only at 50. So there is still work to be done, right? We want to go to 70%. So clearly, the way to go about this is somehow try to get top N so that the recognition improves, and then go and use those top N in your model, or come up with other methods to reduce the lexicon, as in the Postal case, and thereby get your recognition. Okay, so these are the two approaches. So for word spotting, I'm not going to cover, there's a whole bunch of work in image-based recognition, and UMass, Manmatha, and others have worked in this, where you would essentially box out your query from the image and say, show me similar words, and then there is an image similarity thing that is being done, right? Then you could also actually recognize, make it into text, and then do the comparison in the text domain. So that's the one that I'm going to talk about. We have worked in both areas. And in those cases, in the image-based, you could also have the query rendered, right? So I type my query, then you make an image out of it, and then go and match that image in the document. So in the OCR-based, the previous work, from what we have seen, was mostly limited to a single writer, and also was using things like word ranks and assumed perfect segmentation, not realistic, right? So we have come up with an integrated model where we will actually look at handwritten word recognition results, deal with imperfect segmentation and recognition scores, which are not true probabilities, but we have a model to work with them. Here is an example. We are working with some medical forms with a local company, where the idea is, you have prescriptions, and the doctors like to write their prescriptions, and then you want them faxed to the pharmacy and then get them filled. So here we are again looking at limited lexicons, right? There's certain kinds of medications, and if I know the patient, then I probably can constrain the lexicon further. This is just to give you an example. These are some results. You can see faxed, poor quality word images, and we do a fairly good recognition on this, given that the lexicons are not very large. So this is about 87% for the about 50 or 60 words in the lexicon. We had another project with the National Science Foundation and the Department of Health, New York, where we were looking at forms such as this. Okay, these are medical forms, and what happens is whenever there's an emergency, let's say there's a road accident or somebody made a 911 call from home, the first responders come, and after taking care of the patient, they have to fill in this particular form. In New York, and every state has a similar form. So in this form, you have check boxes, what is the ailment, is this asthma or, pulse and things like that, blood pressure, name, address. And then there's a narrative field, which has all kinds of medical abbreviations. Now this form is, now what happens today is this form is collected, then it's probably passed on to some government official. At the end of the quarter, they'll make a report, they'll produce a CD with all those images, and it will sit in somebody's shelf, right? So we wanted this to come alive, where as soon as the form is filled, maybe in the ambulance, it can be put on a scanner, and then we can do our recognition on it, so that the hospital can be informed ahead of time as to who is coming and what their history is and so on. And also health officials can sit and say, well, in the last 1 month, how many cases were there where blood pressure patients made a 911 call? Or how many cases were there of allergies or asthmas and so on, right? So this is going to be very valuable. So we looked at some of these, okay, to answer questions such as, find all people who reported asthma problems in New York, how many people with high blood pressure are on medication X? So you could answer questions such as this. And in order to do that, we had to look at the narrative field and do some keyword spotting, right? And here the spotting is that I have to go through this and pick out words from a larger medical dictionary and saying this must be a medicine name, or this is a name of a disease or something else, some other problem, and then label this particular form, index it with those terms. So here our approach was to somehow reduce the lexicon, and to reduce the lexicon, do some kind of topic categorization. We used a bootstrapping method where we said, without looking at lexicons, what recognition can I do? So we just tried to recognize a few characters in every word. Okay. Now, based on those few characters, we were then able to say that these particular forms are of a particular category, and then use a lexicon corresponding to that particular category to do the next stage recognition. So the lexicon free recognizer, topic categorization, and we got about 7 to 10% jump in our recognition. But still, so it moved in the medical case from about 25% to about 35%. Still long ways to go. Okay, and we used standard modeling techniques such as this. So we look at the topics and the probability of these terms in different topics. This is the result. So as I said, error rate came down, and we got about 7.5% jump. Okay, the T in these columns means we included the truth manually. So this is the real case. In the other cases, you actually went ahead and put the truth in. So we also looked at some other methods, for dealing with medical forms. And here the question is, I have a query, okay, and this is the text from the narrative. Now I want to incorporate the fact that you can have different gaps between words and within words, okay. So how do I model that? So given WR is my observation, C3, C4, these are the connected components. So I look at all the connected components, 2 at a time, 3, 4, 5, 6, and so on. And I will essentially look at sigma as the word gap. So look at it as a probability. I'll show you how it's modeled. So we come up with a formula such as that for similarity. So the word gap probability is integrated. So here these are three different features. So you have, for all adjacent connected components, you have boxes. Look at the median distance or the run length distance, or make a convex hull and look at the distance between the centers. Three different features. And then you, on your training data, you see which of those were actually valid, given that feature vector, those three features. And you come up, so whenever in the test case I see a gap, I can tell you what is the probability for that gap to be a real world gap. And we do the same thing. We have a background model for looking at the scores returned by word recognizers and converting them to probability. So S is the score, so we use what is called the universal background model. Okay, so that, I don't know how I'm doing on time. I'm not too fast. Oh, good, perfect timing. So looking forward, so what I did was I just sampled a few things from our lab. It's clearly difficult to talk about everything that we have done over 20 years. But I think you can get a sense that, you know, we have the background in this area. Forward looking, we are looking at projects where perhaps you can have a document, you know, and then the cameras are on the ceiling, and I'm making annotations on the document, marking them up. So not only do you get my hand gesture movement, you also get the offline image. And using both of them, you figure out where in that document. Now you would know from my desktop what files I have, which document it is, which page I'm looking at, and so where I'm making the marks, and those could be automatically transferred to the document. So ambitious goal, but that's something that we would like to look at. We've also done some work in captures using handwritten words. Okay, so we would like to look, and we have published in this area. I'm just giving you one view graph to describe this. So here you have to understand the English, you have to read English handwriting, and then you have to look at the answer. So my thing could be, she teaches us English, what does she teach us? And the answer, machines probably wouldn't be able to answer that. And we put some marks over there to make handwriting recognition which are more challenging. So we have worked in this. And this is our new project that we are all very excited about. And this is where I hope to join hands with Google and see if we can do something. We are putting together an NSF proposal also on this, is to have something like a science circle. See, today the tablets are so popular. So we are expecting professors would have tablets, students have tablets. And once you have tablets, it's handwriting which is more convenient. So I have a tablet and I find it, I can do this thumbing texting thing quite well. But this is not that convenient, right? So I would just like to draw things and write things. And we would like to have a community of science so that, for example, I'm interested in machine learning and I could post something just like people post today on Facebook or some other social groups. Pictures, we'll just post some notes, right? And then I can have my own community where there might be other people say, oh, that particular problem, you know, this is what I did, why don't you try this, and so on. For all those things, handwriting is going to be absolutely essential. So here's an example. So this is the science circle, like Google circle. We have equations which is going to be difficult to type. So you simply hand draw, okay? And now let's say I want to search, you know, who else would be interested in something like this. So today what you would have to do is you would have to have a query box and you say penicillin and then chemical structure. But that does not capture this document. What you actually need is simply pointing and circling the things that you're interested in. So I would just circle these two and say search, right? And I would need to do recognition of those words. I would need to understand those equations. And I'm looking at probably diagrams, graphs, and so on. So I might give you 3 words and a triangle drawn. If you simply query those 3 words, that does not capture the sense of this document where they were all in a triangle. So I would also like to put a triangle as a query and see what other documents are there among handwritten notes of different scientists. Right? So we can have our own group. So this will have a whole bunch of research challenges like ontologies of these diagram structures, you know, doing handwriting, indexing, and so on. So this is something where we feel, we can do work, so that we can be useful for the tablet users. I'll conclude with acknowledgements. This is, and many more UB students. This I just picked some of my PhD students from the last 5-6 years. Thank you.
Yes, we have 2 minutes for questions.
Where did you get your Arabic data set?
Oh, that is the MatCat data set from DARPA. That particular one. But we have other data sets. I think the IGDAR community has a few data sets for city names and so on, the IEFN data set, and there are a few others. But those examples were from. Okay.
So for the adaptation you're talking about, so if you consider all the features, right, and then you restrict when you do the classification, you just restrict your vocabulary, right? So like you have the example, 2 words, they are similar in the bottom but different in the top, right? So if you consider all the possible features, then the lower part will basically have the feature score. So it should automatically deal with those adaptation issues, right?
True, absolutely right. So, but here the issue was also efficiency. And then there's also the notion of emphasis, right? But you are right. I mean, eventually, if you include everything and let the system decide, that's also possible.
Because like the adaptation also make your training difficult. And then you have data sparseness, right? Because your data will cluster to a small node in your tree, right?
So if you recall, that was a 2000 CVPR paper. So it was like early on where we were still concerned about, training and how fast it will be and so on. The very first system that we actually worked on the research system for the address interpretation, took 4 minutes per address image. Okay, and that was in the lab. And the system that was actually deployed, we had to be at 13 pieces a second. So you can see so we had to make lots of heuristics and lots of pruning and make it more efficient to be relevant for the postal service in those days. So in some sense, if you look back now and if you had to design the whole system today, it would be a totally different system. And that's probably what, Lockheed and Parascript and all are doing. They won't have this linear thing saying zip code first and street number second, because every time you make errors, you're reducing your sweet spot in some sense. So you would go about things very differently, right? Today, because those are not issues. You are not sitting at a terminal for 24 hours to get your program trained. So yeah, so those were the design issues at that time. I thought I could somehow capture that also in this talk as to how things have evolved.